So today's lecture is on chemical reactions. We've talked about atomic bonds, why atoms are bonded together into solids or molecules, into larger agglomerations. But chemical reactions are where molecules interact with each other and the atoms change into different molecules. In other words, they rearrange themselves into different molecules. And there's thousands of different chemical reactions that take place in our world, including in our bodies. There's loads of chemical reactions that happen inside our bodies that contribute to the functioning, that make us dynamic beings. In other words, we couldn't be living beings without these changes that are constantly going on. Here's an example of a chemical reaction, the combustion of methane. A methane molecule has a carbon atom and 4 hydrogen atoms. This reacts with oxygen, which is in a molecular form, 2 oxygen atoms bonded together into a molecule. And these atoms rearrange themselves into different molecules. You get a carbon dioxide molecule and water molecules. So you can see it's the same atoms, the same elements, but the atoms have rearranged themselves into different molecules. Now, one of the things you might notice is that there's more oxygen atoms in the after picture of this chemical reaction than in the before picture. See, there's 2 oxygen atoms on the carbon dioxide molecule and 1 on the 1 water molecule. But over here there's just 2 oxygen atoms, right? Because there's 1 oxygen molecule which contains 2 atoms. And so this isn't really a complete chemical equation. You have to balance it. That means you have to make sure that the number of atoms of each element in the before picture is the same as the number of atoms of each element in the after picture. And you can see that this isn't balanced because look, there's 2 oxygens on the left, 3 on the right, and there's 4 hydrogen atoms on the left in the methane molecule, and 2 on the right. But let me show you how you balance it, like this. So now what this says is the big 2 means there's 2 oxygen molecules that react with that 1 methane molecule to give you 1 carbon dioxide molecule and 2 water molecules. Now you see it's balanced. There's 4 oxygen atoms on the left because there's 2 oxygen molecules, each of which contain 2 oxygen atoms. Over here you have 2 oxygen atoms in this carbon dioxide molecule, and now you have 2 water molecules, each of which contain 1 oxygen atom. So you have 2 plus 2, 4 oxygen atoms over on the right. And also you have 4 hydrogen atoms, right, in the methane molecule. And then later on, those 4 hydrogen atoms appear in the 2 water molecules, because there's 2 water molecules, each of which contain 2 hydrogen atoms. And this balancing of equations, this is one of the things you'll do for the exercise today. These balancing of equations are important because this tells you the relative amounts of the materials that go into this chemical reaction. You know that for every molecule of methane that combusts, 2 molecules of oxygen are used up. And you know that 1 molecule of carbon dioxide is produced and 2 molecules of water. These are called the reactants. The before picture are called the reactants, the things that react with each other. And these are called the products of the chemical reaction, the things that are produced. So I'm going to talk more about balancing of equations after, but let me talk about the energy of an exothermic chemical reaction. When methane combusts, it's a flammable gas, right? Reacts with oxygen so that combustion occurs and you see flame because energy is released. And that's depicted here. Normally you don't put the word energy in a chemical reaction equation, but the fact is energy is released during this. And so why is that? Why is energy produced in this chemical reaction? By the way, this is called an exothermic chemical reaction because energy is released. Exo meaning out of, and thermic meaning thermal energy. It's exothermic if there's leftover energy after the reaction takes place. So why is this energy released? Well, here's pictures of the reactants at the top. a methane molecule contains a carbon atom and 4 hydrogen atoms, and these are the 2 oxygen molecules that each of which contain 2 oxygen atoms. And these are the products: a carbon dioxide molecule with its 1 carbon atom and 2 oxygen atoms, and 2 water molecules. So the reason this reaction is exothermic is because these product molecules have a higher total binding energy than these. What does that mean? If I was microscopic and I wanted to pull apart a carbon dioxide molecule, I would have to pull the oxygen atom off of its bond to the carbon atom. That would take an input of energy. I would have to use up energy to do that because I'm working against the bond that's holding it there. Now if I also took the other oxygen atom off of that carbon atom, that would take some more energy. That energy that it would take to pull that apart, that is called the binding energy of that molecule. And the amount of energy to take those molecules apart, the carbon dioxide molecule and the 2 water molecules, that is the amount of energy that would come out when those molecules form from those individual atoms, right? If I have to put the energy in to take them apart, then when they form back together, that's the amount of energy that comes out. So energy is released when these molecules form. But you might say, but it also takes some energy to pull apart the reactant molecules, right? These things have to come apart so they can reassemble into these different molecules. Well, the amount of energy to pull the reactants apart is smaller than the amount of energy that comes out when the products form. Does that make sense? So there's sort of leftover binding energy. That's why it's exothermic. And chemists like to depict it in a graph like this. It's like you're pushing the molecules up this hill, this energy hill, because it takes some energy to get them apart. But once you get over that hill, it's like a bowling ball rolling down the other side of the hill. It goes further and more energy comes back out. So this energy to get the whole thing rolling is called the barrier potential. And you know that in order to make something burn, like a piece of paper or some methane or gasoline or whatever, you have to light it with a match, right? That's because it takes an input of energy to get some of those molecules apart so they can form into the product molecules. But once that begins to occur, energy is released, which makes more reactants undergo the chemical reaction. So it's like a chain reaction, right? And this energy, they even have the energy listed here, 890,000 joules per mole of methane molecules. That's how much energy is released per mole of methane molecules. Remember, a mole is that big number, 6.022 times 10 to the 23 molecules. So they know exactly how much energy comes out of the combustion of a mole of methane gas. And I think this is a bit like the siphoning of water. I don't know if you've ever done this before, but if you have 2 containers of water at different levels, and you have a tube that's completely filled with water, and you immerse the ends and let it flow, this will actually empty the top container of water. It'll flow down into the bottom. Even though the water has to flow uphill in that first part of the tube, the water going down further in the other part of the tube, there's more force, so it's pulling that water uphill to make it go to the lower level. So this is a bit like the barrier potential in the reaction of methane, why it's spontaneous and acts like a chain reaction. Now, that chemical reaction equation is a sort of a simplification of what's going on in that chemical reaction. A lot of things are happening when the atoms are moving around. It's just the before picture and the after picture is that chemical reaction equation. Here's a little bit more detail as to what's happening in this chemical reaction. Lots of different sub-reactions. The molecules are changing in many different ways. I don't know how they know all this, but in most chemical reactions it's actually pretty complicated what happens between the before picture and the after picture. But the bottom line of that is, you know, the molecules of the before picture turn into the molecules of the after picture. But I just showed you this because I want you to show you that there's a lot of details in this that are going on behind the scenes. Now, this idea of balancing equation, this tells you the relative quantities of the reactants that go into the reaction and the relative quantities of the products that come out, so that you know for every 1 molecule of methane that's used up, you need 2 molecules of oxygen, and that produces 1 molecule of CO2 and 2 molecules of water. But you could just as easily say, well, that for every 1 mole of methane, you're using 2 moles of oxygen, which gives you 1 mole of carbon dioxide, 2 moles of water. Remember, a mole is that big number, 6.022 times 10 to the 23. They invented that, they use that number because on your periodic table, the mass, the molar mass, that's the mass of 1 mole of those atoms. So the molar mass of carbon is 12 grams, right? That means you measure out 12 grams of carbon, you've got that many atoms of carbon. So what is the molar mass of methane? Well, in 1 mole of methane molecules, there's a mole of carbon atoms, that's 12 grams, and there's 4 moles of hydrogen atoms. That's 4 grams because the molar mass of hydrogen is 1 gram. So the molar mass of methane is 16 grams. So you could write this like this: 16 grams, for every 16 grams of methane that's used up in the combustion of methane, you need 64 grams of oxygen, and that gives you 44 grams of carbon dioxide, 36 grams of water. So you see what I've done here. Oxygen, the molar mass of oxygen is 16 grams. So the molar mass of molecular oxygen, molecules of oxygen, is 32 grams, because each oxygen molecule contains 2 oxygen atoms. And so 2 moles of oxygen molecules is 64 grams of oxygen, right? And I've just calculated the molar mass of CO2, it's 44 grams, and the molar mass of water is 18 grams, right? Because it's 2 hydrogen atoms, that's 2 grams, and 2 oxygen, that's 16. So this is a little bit more useful for somebody that has to work with these chemicals. It tells you you're not going to count molecules going into it, right? But you can weigh the quantities of substances that are going into it. So somebody that's going to use methane in combustion of methane. So for example, most of the electricity that we have in Atlanta is generated at a natural gas powered power plant that is down by the Chattahoochee River. That's partly methane. Methane is one of the gases of natural gas. There's other hydrocarbon gases that are in that. But those engineers down there, this is an important bit of knowledge. For every 16 grams of natural gas, there's about 64 grams of oxygen that's being consumed down there. This is also, the fact that so much more oxygen is used in the combustion of methane and other hydrocarbons is actually fortunate for us. When you load your car with gasoline, that's also a hydrocarbon. It's like CH18 mostly. And so for every gallon of gasoline you load into your car, there's many gallons of oxygen that your engine breathes from the atmosphere. Where does the oxygen come from when your car runs? It sucks it out of the air. We get that for free because the plants of the world happily produce oxygen during photosynthesis. So most of the chemicals that you use to run your car actually come from the air. You have to buy the gasoline, but the oxygen comes free from the air. That's one of the things that makes the combustion of hydrocarbons attractive for the production of energy, because most of the chemicals that you're using actually you get for free. So let's do a few more of these balancing of chemical reaction equations. So here's another chemical reaction. Potassium nitrate reacts with, I think this is called carbonic acid, to get potassium carbonate, and this is, I believe, nitric acid. So, okay, so we want to make sure that the numbers of atoms of each element on the before picture on the left side is the same as the number of atoms of each element in the after picture on the right side. And the first thing I see when I look at this is there's 2 potassiums in that potassium carbonate, right? Because that's what that 2 means. But there's only 1 potassium atom on the left. So why don't we put a 2 there? Now that I've balanced out the potassium, but now I've unbalanced some of the other things, because now I'm saying there's 2 molecules of potassium nitrate. That means there's 2 molecules of nitrogen and 6 of oxygen, right? Each potassium nitrate has 3 oxygen atoms, and now there's 2 of them, so there's 6 oxygen atoms. So combine that with the 3 oxygen atoms in the second component. There's 9 oxygen atoms on the left, but there's only 6 on the right, right? So I've unbalanced the nitrogen and the oxygen. But if I look at the carbonic acid, it's got 2 hydrogen atoms, right? Over on the right there's only 1 hydrogen atom. What if I put a 2 there? Now I've balanced out the hydrogens, right? And serendipitously, I've also balanced those other 2 things, because now I have 2 nitrogen atoms, because there's 2 nitric acid molecules, each of which contain 1 nitrogen atom, and that balances out the 2 nitrogens over on the left. And now here in this nitric acid there's 6 oxygen atoms, right? Because there's 2 molecules, each of which contain 3 oxygen atoms. So that's 6. Here's another 3 oxygen atoms. And so that balances out the 9 on the left. So this is a balanced equation. So this shows you the relative amounts of the molecules of this in this chemical reaction. Okay? Hopefully this is getting clearer. Let's look at another one. This is the oxidation of aluminum. This Al over here means metallic aluminum. Aluminum, all by atoms in an aluminum metal. And this is molecular oxygen, again, molecules of oxygen, each of which contain 2 oxygen atoms. And that forms Al2O3. Well, when I look at this I see the 2 on the aluminum, so I say, well, let's put a 2 over here. Okay, that balances the aluminum. What about the oxygen now? Well, there isn't any integer I can put in front of that oxygen, that O2, that'll balance it, because if I put a 2 there I get 4 oxygen atoms on the left and there's only 3 on the right, right? So how do I do that? Well, what if I put a 2 there in front of the aluminum oxide and a 3 there in front of the oxygen? So now I've got 6 oxygen atoms on each side, right? 3 oxygen molecules on the left, each of which contain 2 oxygen atoms. 2 aluminum oxide molecules on the right, each of which contain 3 oxygen atoms. That's 6 oxygen. And then of course I've unbalanced the aluminum, so I just switch that to a 4. Alright, so now it's balanced. 4 aluminum atoms combine with the 3 oxygen molecules to form 2 aluminum oxide molecules. So you see, in some of these balancing things you might have to go back and forth and change the numbers a few times. Some of them are harder than others. But this tells me the relative amounts of aluminum and oxygen that are involved in the oxidation of aluminum. Let's do one more. Potassium hydroxide combines with cobalt phosphate to form potassium phosphate and cobalt hydroxide. So now, here this is a little different. We have these parentheses here. What does that mean? Well, the 2 outside this parentheses means there's 2 phosphate groups connected to these 3 cobalt atoms. Okay? This PO4, multiply that by 2. So there's 2 of them, 2 of these phosphate groups on these cobalt atoms. Now the reason they write it this way, you could just as easily write this CO3P2O8, because that reflect the number of atoms in that molecule. But the reason I write it this way is because oftentimes in a chemical reaction that phosphate group just stays together. And you can see there's phosphates connected to potassiums on the reactant side, or in the product side of the arrow, right? And for a chemical reaction equation like this, the easiest thing to do is look at that phosphate group. That's got a 2 there, so why don't I put a 2 next to this? Now I've got 2 phosphates on the left and 2 on the right, right? So that partially balances this thing. And what about potassium atoms? Well, I've got 2 potassium phosphate molecules on the right, each of which has 3 potassium atoms. That's 6 potassium atoms. So what if I put a 6 over here? 6 potassium hydroxide going in. Okay, that balances out the potassiums. But now I've got, look at the hydroxides. This hydroxide is another one of these groups that can stay together during a chemical reaction. I've got 2 of them over here, 1 of them, and 6 of them over here. So what if I put a 3 there? So that balances out the OHs, right? And serendipitously, I've also balanced out the cobalt, because now I have 3 cobalt atoms over here, 3 on the left in that one molecule. All right, so this one is now balanced. Okay, so hopefully this will clear things up a bit, and you can get started on that balancing exercise.